In this work, we propose collision-inclusive manipulation planning for occluded object grasping via compliant robot motions. Traditional manipulation research mostly focuses on collision-free problems. However, many practical manipulation tasks actually require collisions to achieve the desired task configuration. For example, as shown in the bottom figures, to grasp a book lying flat on a table or from a shelf, the desired grasping configurations are occluded by the table or the surrounding books. In such scenarios, a collision-free solution does not exist, and the robot has to make collisions with the environment to achieve a grasp. By enabling compliant motions, the collisions between the robot and the environment become available, and can thus be exploited. However, this will introduce more dynamics into the system state transitions, and hence more physical uncertainties due to inaccurate modeling. In this work, we propose a collision-inclusive planning framework that can transition the robot to a desired task configuration without accurate system modeling or accurate perception. By effectively exploiting environmental constraints via compliant robot motions, the physical uncertainties during real executions can be reduced. Furthermore, by exploring a conceptual manipulation funnel through task repetitions, our proposed framework produces more stable manipulation outcomes. As an example, grasping the book in the middle of the stack, the poses of the books are estimated via an off-the-shelf visual model. The workspace is then discretized to a 3D grid. Through an A-star algorithm, the positional path for the task frame, as shown by the green lines, can be found to exploit environmental constraints. Guided by the computed positional path, the geometric path of the pose of the task frame will be refined by minimizing the collisions between the robot gripper and the environmental objects. Based on penetrations of the robot gripper into the environment, the external forces will be estimated for each waypoint in the geometric path to very roughly approximate the system dynamics. By solving an optimization problem constrained by the approximate dynamics, the Cartesian impedance controls represented by the red trajectory of equilibrium poses of the task frame will be solved and commanded to move the robot. After executing the impedance controls, if the task is not accomplished, replanning will be launched starting from a random valid pre-grasp configuration for task repetitions until the desired grasp is achieved. In real executions for grasping, we found that our framework can exploit environmental constraints in different ways depending on the initial task configurations. The green lines are the geometric path of the task frame to effectively exploit environmental constraints, and the red lines are the trajectory of impedance controls commanded to move the robot. For example, in the left video, the environmental constraints were exploited via contacting the support table surface, whereas in the right video, the robot exploited the object's surface to facilitate the task. We select 9 objects in different sizes and weights for real-world evaluations and tested our framework on both single-arm and dual-arm setups. To challenge our framework in different realistic scenarios, we tested our approach to grasp a single object on a flat surface or from different locations that are occluded by other objects. With a single Franca Emica Panda manipulator and an artificial aluminum frame to partially constrain the object's motion, our framework can enable the robot to successfully grasp the target object, typically within one trial. In a dual-arm setup, the second arm moves to block the object from the other side to prevent it from being pushed away. Such a dual-arm setup more realistically challenged our framework without any artificial constraints. However, our framework was still able to successfully grasp all objects. By making collisions with surrounding books to create free space, the robot could successfully grasp the middle target book from the tray, which was initially infeasible. Similarly, our framework was also effective in grasping the object in the middle with other objects stacked beneath and over it in a dual-arm setup. Although the task was not accomplished on the first try, the task repetitions as desirably contained in a conceptual manipulation funnel always produce stable outcomes and eventually achieve the grasp. And finally, in a very confined space like a shelf, our framework was still successful in achieving grasp success even in this historically difficult task for robot manipulation. In addition, for performance comparison, we selected a relevant baseline and adapted its implementation to our task setup. Some example executions of the baseline are shown in the videos. Compared to our method, the baseline was more susceptible to system dynamics and more often led to failure with incorrect grasps. Overall, the authors are excited about this work and the manipulation capabilities it achieves. We would like to acknowledge our funding sources and thank you very much for watching.